Hi everyone. First, a little bit about me. So I'm a programmer, backend, front end. I like all of it. In particular, I've enjoyed working with Scala, Dart, TypeScript, and in the past I've worked for Twitter and Signal Messenger, and also at tech companies, startups. Um, that's mainly what I've done in the past. And currently, I work for Dasera, which is a security company focused on protecting or helping companies protect user data. And it happens to be that Dasera is looking for awesome Scala engineers. So if you're interested, get in touch. Okay, so my talk today is about actors and using actors in Unison. But first, a little disclaimer. I'm not any sort of expert or authority on actors. The only reason I sort of started working with it was because when I wanted to make a video game backend, I found it to be too difficult using the typical functional programming approach of streams and resources and all of that stuff, the structured concurrency. And I thought actors seemed simpler to me. So maybe since I'm not that good at putting together something with the more traditional FP, I can try actors. So that's why I wrote the actor library, just sort of as an experiment to see if I could make this video game backend. So what is an actor? It's a way to model concurrency where you have many independent single-threaded processes communicating asynchronously with each other. The nice thing is the sort of independent part, because you can focus on the one actor and really understand its behavior without having to think necessarily all the time about the entire system. And then separately, you can start thinking of the entire system. So in a way that made it simpler for me to understand. It can receive and send messages. It can only do one thing at a time. It's a single threaded. And it can only communicate with other actors by sending them these asynchronous messages. An actor is made up of a description of its behavior, or like the instructions that the actor follows, and the state while it's running. And it can, based on the messages that it decides to process, it can decide to change its state or even change its behavior. Yeah. Another nice thing is that this model fits sort of naturally with how a lot of things in the real world work. So it makes for a very nice way of simulating real things. So an actor can be in a particular state. So if it's in the process of dealing with a message, it's running. If a new message arrives while it's processing a message, the message just gets queued up in its mailbox. And once it's finished processing that one message, the actor can choose to process another one or do other things like take a nap. Basically, it can decide for 5 minutes, I'm just going to not process any more messages. I'm going to wait. And while that's happening, any messages continue to queue up on its mailbox. Another state an actor can be in is it can be waiting because it has no messages. So it's waiting for a message to arrive. Okay, so what is a message? A message is basically anything. It can be a Boolean, string, or any sort of data type that you create. It can also be functions. It could be a callback, or any or a thunk. And it can also be a reference to another actor, or a list of references to other actors. And that's very important because that's how actors are able to understand how to communicate with other actors by sending these references. Let's see. Okay, so the life cycle of an actor, it spawns something, spawns it. It would be another actor decides, okay, I'm spawning this actor with a particular behavior. Then this actor can be on one of those three states. So it can receive, it can spawn other actors. It can wait a certain amount of time before doing anything. I think of it as taking a nap. It can send a message to another actor. And in the particular implementation that I'll go over, it can also log a message to the console. Or not necessarily to the console, but log a message to the system that the system can choose to render it in the console or in some other way. And it can also perform I/O if it needs to save information to a file or read from a database or something like that. And after the actor has completed its behavior, it expires, it dies, it no longer exists, and any messages that you send to it won't be received, won't be processed. But an actor can also choose to continue doing a behavior. Maybe as part of its behavior, the actor goes into an infinite loop, and that's fine. Maybe the actor's job is to serve as a timer, so it continues waiting, signaling to some other actors some information, then waiting again. So in that sense, it could live for an indeterminate amount of time. Okay, so the behavior of an actor in Unison looks something like this, using the library that I created. So it's a thunk. Here you can see that it can log something. It can wait some number of seconds. And during that time, the actor is just in this waiting state. It's not doing anything. In this case, it's deciding to spawn a new actor, which is calling the child, waiting 4 seconds, then sending the spawned actor, the newly spawned actor, a message. And then, without waiting for a response, because it's an asynchronous message, it's logging that it is done. Sort of like this is the basic template for an actor behavior. It demonstrates the type of operations that it can perform. So drawn out, that process looks a bit like this. So it's in the here you can see that it logged that it started. Then it's waiting for 6 seconds, spawns a new actor, which you can think of it as another thread of execution. After it decides to wait for 4 more seconds, and it sends a message to it. And then at this point, this particular actor dies because there's nothing more in its behavior for it to continue doing. Okay, so with the basics out of the way, I'd like to move on to doing some live coding, so we can explore how would you use this to implement some sort of simulation or write actor-driven code. Let's see. Yeah, here. Actually, I gotta clear this real quick. Okay, so first we'll create a main function. Just to verify that this is working, we'll say run main. Main is running. Okay, so the first step is to create our top level actor. So we use the actor dot there's several functions we can use to create our first actor, our top level one, but we'll use one called run sync. And it takes the name of the actor. So I'm just going to call it system. And then within, and we give it a thunk. And within this thunk, we can do all the things that an actor can do. So we'll just log started. Done. We'll just run that really quick just to see what we get. Okay, and you can see the logs get nicely prefixed with some timestamps and with a marker. Okay, the simulation I was thinking we could do is an office that had a few programmers coding away, working on something. And then we can see how they would interact, or what would happen. We can start with just that. We have, let's say, two programmers coding away. So I'm going to start by spawning the first one. I'll assume I'm modeling myself programming away. We'll use the same name. It work. And we'll create another one. If we run that, we can see that both were spawned. And something a little strange happened here. We can see that the system actor logged that it was done before even either of these actors started. And the reason is spawning an actor is also an asynchronous operation. So it's the actor was spawned, tasked with doing something, but the top level actor that spawned it is not doing any waiting. Immediately after it spawned them, it signaled it's done. Okay, so that makes sense now. Of course, we don't want to have this behavior duplicated, especially once it gets more complex. So we'll move it to somewhere so it can be shared. We'll call it the programmer behavior. So now I can do programmer behavior. And the same thing should work. Okay. Now let's say this, the concept I wanted to explore is, as these programmers are working, their energy is being depleted. So let's say we start out with an energy of 50. And then say, or let's define it above. Working, we're going to log that is working and how much energy it has. Let's do this. Okay, but we need to deplete the energy. So this actor needs to start keeping track of changes to its energy. What we'll do for that is create a thunk, or not a thunk, a function that will determine the rest of the actor's behavior and how it starts to deplete its energy. So I'm going to call it behavior. It will take the energy as a parameter. That will be the starting energy. Then it will log its current energy. Then we'll simulate the fact that they're working by actually having them wait. Wait 2 seconds. And then we want them to continue working but with their energy depleted by some amount. So we'll do behavior energy minus 10. Okay, so we've defined the behavior of the actor, knowing how much energy the actor has, but we need to kick it off. So we'll start it off. We'll just say the starting amount of energy is 50. But since we're recursing here, this actor will never stop, which is fine for now. We can test it. Okay, and now we can see two programmers working away, and their energy is getting depleted as they work. Okay, let's add one more thing here, just to sort of simulate the fact that one actor arrives, or one programmer arrives to the office. Yeah, actually, we'll call this the office. One actor arrives, or one programmer arrives to the office a little bit later. So, well, before we spawn the Alex programmer, we'll wait a few seconds. Wait 3 seconds. Spawn the Alex programmer, and then see what that looks like. Okay, you can see that the Alvaro programmer started working. His energy started getting depleted. And then Alex arrived and is ready to work, and his energy is getting depleted. Okay, but once the energy is depleted of a programmer, they can't continue working. So let's update that to simulate the fact that they don't have any energy left. So we'll say if energy is less than 10, say less than or equal to 10, okay, we'll say that this actor or this programmer is too tired. They cannot continue working. Else, we'll continue this sort of log work loop. Okay, we can see their energy getting depleted. Okay, first programmer is too tired. Then the next programmer is too tired. Their behavior ends and the simulation stops. Okay. Now let's figure out a way to get these actors, these programmers, some more energy. And the way I get more energy is by drinking some coffee. So we'll create another actor, and we'll call it the coffee maker. And I think I'm just gonna, for now, inline the behavior of the coffee maker. So the way I'm envisioning this is that once a programmer is too low on energy, they will ask the coffee maker for some coffee. So we won't write the behavior of the coffee maker yet, but we have to figure out how can the programmer ask the coffee maker for some coffee. It needs a reference to this coffee maker. But since the behavior is defined outside of this function, of the scope, it doesn't have one. So the key is to just pass the reference to the coffee maker to the behavior of the program. So we'll do coffee maker, and this is just the reference to the actor. And then when the programmer gets too tired, it will ask for coffee. Coffee maker. We'll send it a message. Coffee, please. Okay, after it asks for coffee, it needs to. Well, actually, let's do the coffee maker first. So right now it will ask for coffee, but then it will end its behavior. We'll have to fill that in a minute. First, we'll do the coffee maker. So the coffee maker can receive a message. So we'll say, call it, let's call it message. And this is how it receives a message. Well, first let's log that it started, just so we can see it. Okay, it receives a message, and then we can take a look at the message. And we'll say if somebody's asking for coffee, we'll do something. Here we'll do something. Otherwise, we won't do anything. Okay, if they're asking for coffee, we'll say we'll start making some coffee. Then we'll simulate the fact that it takes time. So we'll wait. We'll just wait 1 second. Okay, we're making coffee. Coffee is ready. Let's say coffee is coffee is coffee. But what do we do with the coffee now? How do we get this coffee to the programmer that requested it? Since we don't have access to that, a reference to this actor. Well, the key is to, when the programmer requests coffee, it needs to signal to the coffee maker who to return the coffee to. And the way we do that is just by including a reference to this actor in the message itself, kind of like a return address for the message. And the way you do that, so instead of the message being a string, we'll make it a pair, where the first part is a string and the second part will be a reference to the programmer actor that is requesting the coffee. We can do that with self. So now when we go back to the coffee maker behavior, we won't be matching on just a string. We'll have to match on this, and also the coffee drinker, which will be the reference to the actor that asked for the coffee. So now that we have this delicious coffee ready, we can send it to the coffee drinker. Coffee drinker, send coffee. Okay, so this right now sort of makes sense for the behavior of the coffee maker. Now the programmer needs to be able to receive the coffee. So we'll just say coffee receive. And now you can say we'll log what it received. So I'm drinking coffee. And let's say drinking coffee takes a second. So wait seconds. And after some amount of time, the energy of this programmer is back up to full. So it will continue his behavior with a full amount of energy. I'm using 50 for full. Okay, let's see what this looks like. First, I guess let's fix some bugs. Looks like we're missing a parameter for programmer behavior. Oh yes, we have to pass when we spawn the programmer. We need to now pass it the reference to the coffee maker. So we do coffee maker, and since the spawn takes a thunk, we just create a thunk where the first thing in the thunk is to start the behavior with the coffee maker as a reference. And we do the same for this one. Okay, that seems to work. Let's try running it. You can see Alex is ready to work. Both of our energies are getting depleted. Oh, I got too tired. So I asked the coffee maker to make me some coffee. I drank the delicious coffee, and I'm back working again with a full amount of energy. Okay, but Alex is too tired, but there's no coffee. Well, the problem is the behavior of the coffee maker is to receive one message, decide what to do based on that message, and then end. Not quite what we want. We want the coffee to continue receiving coffee requests and preparing this coffee. So we'll wrap this. We have to wrap it here. Let's wrap it. Assuming that the coffee maker can only make a certain number of coffees, let's say we're going to repeat this 10 times. So the coffee maker will loop essentially through this 10 times as long as there is a coffee request in the queue for it to process. If there isn't one, it will just wait there until the next request comes in. Okay, let's just make sure it runs as expected. And I can now see that the coffee maker is making coffee again every time that one of the programmers is too tired. And once the programmer receives the coffee, they are able to resume working with a full amount of energy. Okay. I think that's sort of gives you a sense of how to program with like the simple way you can model something using actors and just functions for the behavior where it keeps recursing while updating the state. Okay, now looking at these logs is good, but I really want to get a better sense of what's happening. And the nice thing about Unison abilities, or one of the nice things about Unison abilities, is that the way this actor system is implemented, it depends on abilities, and I can use abilities to define how I want my my simulation to function, but I can defer the actual running of the or evaluation of the ability to a handler. This particular handler performs this sort of runtime behavior. But let's say I wanted to run through the simulation and see it graphically as a sequence diagram. So all I have to do is create a different handler for the same code that it decides to evaluate all of the actor ability functions in some different way, still maintaining the semantics and allowing the actors to receive information the way they expect it, but it won't necessarily do this. It will do something different. So I created one called run to doc. And I haven't tested it with this one version, so we'll see what happens. But the idea is that this um, this handler will take in any of the, will basically run through the simulation and produce a sequence diagram. Oh, I don't think I can do IO here, so I'll just remove that. Okay. And I'm hoping this works. Let's see. Oh, in order to see it, I pull up the very nice Unison local UI. Actor doc. And yeah, it does work. Great. So the way this handler evaluated the simulation was to produce this sequence diagram. Now you might think, how come it was able to do it so quick? Because it didn't actually last as long as the previous simulation that we ran. Well, since a lot of the things that the actor does is implemented through abilities, this particular handler chooses to fast forward through time in order to skip through all the waiting that would normally happen. But as far as the actors are concerned, as far as they can tell, they're running normally. There's no fast forwarding. So if one of these actors requests the time, they will get the fast forwarded time without realizing it. Okay, so I think this is really cool that I can see this in share, in the local UI in share, but it has some limitations. This is using a sequence diagram that Mermaid supports. It's not really designed for showing actors. It's not aligned to sort of any time scale. So it's a little bit difficult to compare the times when certain events happen. And it's also static. What I would really like to see is an actor running live in real time. So I created another handler called run this that will actually send the events as they happened, all the information about the actor's system as it happens, to another application that is able to render the simulation live. So that other application is written in Flutter, so I'm just gonna start it, and then I can connect to it using this run this. Okay, and if I remember right, it takes a host name and a port. And I have to wrap it again in a main function. Well, there's the application. Okay, I should be able to run it now. Run. Oh, I forgot one thing. I need to make sure that the main function doesn't die before the simulation completes. So I have to do sleep duration, and let's do 40 seconds. Oh, there we go. And you can see as the actors are communicating with the coffee maker. Oh, and also you can see how the Alvaro actor started before the Alex actor. And you can see the messages, requesting coffee, the coffee maker making coffee, taking some amount of time, and that's running live. And okay, I think I'm out of time, so I think that will be the end of my talk. Thank you very much.